Welcome to the lecture number 2 of ray optics, where we are going to start off with spherical mirrors. Basically, concave and convex mirrors, the entire scratch to concept to application to PYQs. In today's class, we are going to discuss the different characteristics, important terminologies of mirrors, curved mirrors basically, then ray tracing, sign convention, mirror formula, magnification, moving objects for concave mirrors, convex mirrors, the graphs and PYQs. All of this in today's class. I hope you are ready, geared up. Last lecture we had done flat mirrors, plane mirrors and amazing concepts of deviation, multiple mirrors, multiple images formed by inclined mirrors, moving mirrors, all these things done in the lecture number 1. This is your Captain Shreyas, and gear up for today's class because it is going to be as exciting as always. Cool? So, my name is Captain Shreyas. I am the physics master teacher. I have been training kids for the past 13 plus years and guiding, mentoring, teaching, making sure that I am a part of your journey right from the time you decide you have that dream to the final reality where you click a selfie in front of the IIT, right? So gear up, guys. I myself did my BTech from IIT Nagpur, did my research from IIT Bombay, and I really hope that I produce really amazing engineers, scientists, and future generation entrepreneurs from this particular channel. Thank you so much. If you have not yet subscribed, please do that, and also like the video. And if you have not yet registered for MVSAT, please do that. Today and tomorrow, last days for registering to get a free gift. What is that free gift? JEE Advanced Rank Accelerator book. In case you do not know what that book is, that is this one. If you register today and tomorrow, you can register via multiple accounts, so your chances will improve. The lucky 2 winners are going to get this particular book couriered at their doorstep. 2 winners. Okay, so take your chance, guys. Go all in, all out. Yeah, 4th, 5th, 11th, and 12th of October. Let's begin. Right. Hi Rohit. Hi Dark Knight. Hi Rama. Good evening. Uh, yes, Deepan, this is good enough, not just for mains but also for advanced. Rama, nice to see you too. Thank you so much, Dark Knight. Means a lot. Means a lot, guys. Okay. So for some reason we were not able to conduct this class on Tuesday, so that's the reason why I kept it today, so that I wanted to finish this off, and then yes, today's 11th standard class we'll do it next Monday. Okay, so slight change in timings, apologies for that. Anyway, spherical mirrors, basically any mirror which is curved, any mirror which is curved, and maybe it will have some silvered surface. This is nothing but a curved mirror. This is nothing but a curved mirror. And if you now visualize this particular mirror, maybe it is a part of a big sphere over here like this, and maybe this particular mirror over here is a part of this particular sphere over here like this maybe. So depending on which surface is silvered and which surface is not, I can say which one is concave and which one is convex. Like you can see, the shaded part is on this side. So this is the exposed surface. So this particular mirror is nothing but a convex mirror, because if light rays come, they will be reflected from this side over here. If the light rays fall over here, they will be reflected over here. So this is a convex kind of a mirror, and in this scenario you will see if the light rays fall here, they will be reflected like this. The light rays fall here like this, they'll probably be reflected like this. So this kind of a mirror is then called as the concave mirror. Concave mirror, because this curved surface is a part of a sphere. That is why sometimes it is also called as a spherical mirror. And I will show you one such spherical mirror, which I have it with me right now. Okay, so you can see this is a spherical mirror. This mirror is a part of an imaginary big sphere. Yes, it will have a huge radius. You can imagine the surface will be like huge. It's a big sphere. There is a small curve in here. I don't know whether you can see it. You cannot see it obviously through the camera, but I can feel it when I touch it over here. And I can sense that the curvature is, not like too curved. It's almost flat, but there is a small bend in it. And that bend, if continued, then it will form a big sphere here, which I then consider this is a spherical mirror. It's a part of a sphere. That's why spherical mirror. Is this absolutely very clear, my dear warriors? Everybody with me? Yeah. Yes, Dark Knight, just 1,000 more people, less than 1,000. All right. Cyclotron not needed. Yes, droppers also can see it, definitely. Sir, can we find the radius of the mirror? Yes, definitely. You can find the radius of the mirror, the center of the mirror, everything. And that is what is going to lead us to locate the image and its nature. All right. Just a quick recap of things. Whenever rays actually meet, that particular location will have the concept of real image or real object. But whenever you have to extend the rays, so that they do not actually meet, you had to extend them, then that place is nothing but virtual space or virtual image. Keep that in mind. Okay, just a quick reminder, this is what we had done in the previous lecture also. Okay, so now that we understand concave and convex mirrors are part of spheres, so I have shown that imaginary sphere here as well as here. This is the actual mirror. That actual mirror is over here or here. Remember, it is in 3 dimension. Here we are just showing one curve, but actually that curvature will be here also. You can visualize that curvature will be like this and go behind also like that. It will go like this, like this, like this. It's like a 3-dimensional figure, but we have shown it in 2 dimension. That's something which you should notice. The center of the mirror is called as the pole. Standard definitions, I'll quickly write it down over here. P is basically the center of that particular mirror. It is called as the pole. So for this particular mirror over here, this point here, this is the center of the entire mirror. This point is the pole. Okay, this point is the pole. If I draw the center of curvature, meaning the sphere's center might be somewhere over here. Okay, it's a part of a big sphere, right? The center could be somewhere here. A line passing through the center and the pole, that is called principal axis. So C over here is basically the center of curvature of that particular sphere or spherical mirror. The line which passes from P to C, that particular line is then called as the principal axis. The principal axis also divides the mirror into 2 parts, up, bottom, left, right, whatever you want to say. So right now this pen represents the principal axis. I hope you are able to visualize. Up, down, left, right, this. So you can see equidistant from all the sides. Okay, so it is exactly the perpendicular drawn to that mirror, passing through the center and passing through the pole. It is like a symmetrical axis to the mirror. Okay, it is like a symmetrical axis to that particular mirror. Okay, now if you take a convex mirror, you will see the rays which fall on it will diverge. They will basically diverge. So it is diverging in nature. Diverging in nature. But the same rays on a concave mirror, when the parallel beam of light is incident, they will reflect and converge at a point. So it is also called as a converging mirror. Converging mirror. The point of convergence F is called as the focal point. The point of convergence F is called as the focal point. Keep all these things in mind. Okay, the point of convergence or divergence, wherever the rays attempt to meet or actually meet, is called the focal point. All these are basic terminologies. Okay, now having said that, let us also define the radius of curvature over here. So we have our imaginary sphere, we have the center of curvature, we have the pole, everything is shown over here. So if I draw a distance measuring from center to the pole or center to any point on that sphere, this particular distance is the radius of curvature. This particular distance is nothing but the radius of curvature. Okay, this is nothing but the radius of curvature. Okay, so R is the radius of curvature, radius of curvature, and this particular radius of curvature is definitely related to the focal length. Now, wherever the rays meet from the pole, if you measure that distance, that is the focal length. So I will put this particular small f over here. Small f is also called as the focal length, focal length, and it is the distance between f and p. It is the distance between, it is the distance, it is the distance between the focal point and the pole. It is the distance between the focal point and the pole. So if I have this particular mirror, the rays are falling and they converge here. So from this point to the mirror, that distance is called as the focal length. F is the focal length, not focal point. Focal point is capital F, small f is focal length. This radius of curvature is related to that focal length given by 2 times of f. Now this is a very important relationship which you should know. R is 2 times of f. So the radius of curvature, this particular radius is 2 times of f. This is f, this is f. So strictly speaking, f is the midpoint of P and C. So strictly speaking, you can say f is midpoint, is exactly in the middle of the pole and the center of curvature, of the pole and the center of curvature. Is all these points absolutely clear in your head? Let's go ahead then. Very good. Keep it up. R is 2 times of the focal length. Another important thing regarding the mirrors is the aperture size. This is also interesting. A stands for that aperture. That means, imagine this particular mirror is this much wide. So all that bunch of rays falling in this particular area will be reflected. So this diameter that you see is kind of the aperture. Okay, this particular mirror's size is measured by the aperture. So this A stands for the aperture, which relates to how wide is the reflecting part, is the reflecting surface or the reflecting part, how wide is the reflecting surface. And bigger the aperture, more rays will converge onto it. And if more rays, more aperture, that means the brightness will depend on it. So keep this in mind that if basically more light rays form an image, then it is brighter. So also keep in mind that a large aperture, if you have a large aperture, it directly leads to more a number of rays, which further leads to a brighter and clear image, a bright image which will be formed. Okay, so wider this aperture as compared to a small mirror. Imagine the mirror was not this big, it was this small. Very few rays will converge. It will not be so clear, or it will be visible but not so bright. It will be dim. But when many rays are converging, you can see very good clarity. It will not look faded. It will not look dull. Okay, so that is the meaning of that aperture and the relationship with the brightness of the image. Lastly, whenever we discuss the image formation, the size of the aperture, the size of the objects, images, etc., you will notice that most of the times the objects are quite small as compared to the other things. Also, radius of curvature and all of that. Also, the apertures we do not take very big, like for example, this mirror is quite huge. We don't study such big mirrors. We study little bit small mirrors only, because we want the rays to be close to the principal axis. You might be wondering, why, sir? What happens if the ray is far away from the principal axis? Then the derivations, assumptions won't hold true. There are some derivations through which you get the formulas. Those formulas make use of some assumptions, like the rays are very close to the principal axis. So that is called paraxial rays. So the rays are close to the principal axis, making small angles, As a result, what happens is, there are some approximations which are done. Whenever you have small angles. Sine theta is theta, cos theta is 1, tan theta is sine theta, which is theta. Some approximations which are made in the derivations, and from that you get all your formulas. So we don't really consider big mirrors or those rays which are very far, making big angles with the principal axis. So those rays which are close are called as paraxial rays. Okay. Yes, we'll be doing questions also, dark night, definitely. Okay. All right. You never had a word paraxial, so now you heard it. So keep this in mind. Also, one more thing. We consider paraxial rays for a particular reason. One more reason. We also neglect, we also neglect spherical aberration. These kind of words are very important. They can come in statement based questions even in JEE Mains and other examinations. Spherical aberration. We neglect the spherical aberration. Now, what is this spherical aberration? See, if there is a parallel beam of light, the rays should meet at a point. But it doesn't really happen in a spherical mirror. You will see that the rays actually meet at multiple points. Let me explain how. So, say for example, this is a sphere. Oops. This is a sphere. Same sphere. But first time I take a very small mirror. Okay, this is a very small mirror versus a very large mirror. Aperture is huge. Okay, think of it like this. That thin line represents that imaginary sphere which the mirror is a part of, spherical mirror. So this is small versus large. So just imagine this is our principal axis. This is our principal axis. Now light rays are coming onto it and falling, and we want to see where they meet. So if if light rays are coming like this, like this, like this, and like this, you will see the light rays will probably meet over here, maybe like this. And as you can see, they are almost meeting at the same point. Because they are meeting at the same point, so focal length is unique. Focal length is unique. So there is no aberration. There is no aberration or negligible aberration over here. That means all the rays are converging at the same point. But the moment you take a big mirror, the rays are no longer paraxial. This is what you are going to see. This is what you are going to see. Okay, let me just show a couple of rays over here, not more. You will probably see these rays will meet here, let's say. Then let's say this ray will meet here, and maybe this rays will meet here. As you can see, there is no clear focal point. The focal point is different for different rays. So definitely there is aberration. Aberration is there. Aberration is there. The focal point is not the same. This will give you a dull, a blur, not so clear image. When there is a unique focal length, all the rays are converging at the same place. Imagine the rays are converging at different places. So the image will also be formed at multiple places. So it will give you a very shady, blurry image. Is that understood? What is the difference between spherical aberration being present or not being present? Now, to avoid spherical aberration, we do not use spherical mirrors. In reality, we use parabolic mirrors to avoid that defect. So whenever you have a parabolic surface, so whenever you have when the mirror surface is big and you use a parabolic mirror, this is basically parabolic mirror. All right, and this is our principal axis. Then, no matter where you take the rays, here or here, okay, wherever you take it, you will see the rays will exactly meet at the same point. So now there is no aberration. So now you will see there is no aberration. The moment you use what? The moment you use parabolic mirrors. So spherical mirrors, we generally keep it small to avoid that aberration. But if the mirror size has to be big, why do you need a big mirror? Because you want that image to be brighter. Then you use parabolic mirrors, but we do not study in JEE syllabus parabolic mirrors. Got my point? But you have studied it in mathematics, yeah, and you study some brief applications of that normal drawn to a parabola, tangent drawn to a parabola, parametric form, maybe for this reason. So when you go deep dive into optics, that's when you are going to use conic sections and tangents and normals for conic sections for solving those ray optics problems when you do it for higher studies, not now. Okay. So now that this particular theory is complete, maybe we can do some questions on it. You have a concave mirror of certain focal length and you dip it inside a liquid whose refractive index is there. What will the new focal length be? That's the question. Yes. What will be the new focal length? It's a very flop question. It was asked this year, and believe me, many students gave the wrong answer. They thought the focal length will increase or decrease mu times or some 1 by mu times, whatever. The answer is it will not change, it will be f. If you remember carefully, just some time back I told you the focal length and radius are related by this equation. Whether the this mirror is in the water or in the air, how does it matter? The radius is still the same. Refractive index has no role to play in deciding the focal length or radius. So it has got nothing to do with it. It was just a flop, silly question. The answer is just F, nothing else. The answer is just F. Is that clear, everyone? Got it? Pakka? Shall we go ahead to the next part then? All right. Collisions class will be doing it, Dilip, next week because I just wanted to finish off reflection this week. A lot of kids were demanding momentum collisions. I just saw the views also were not that great. I figured out maybe students are not right now studying that chapter. So I just gave some time so that you guys watch that lecture and then come to the second class. Okay. So that's the reason for it. Perfect. Okay. So this is done. Now, let us go to the concept of ray tracing. Let us go to the concept of something called as tracing the rays to figure out where the image is formed. Now see, to locate an image, to locate any kind of image, two rays are enough. two rays are enough for me. Two rays are enough. If there is a third or a fourth ray, I know it will still meet at the same point. It will just give me that additional confirmation. Two rays are more than enough for locating the image. And we can locate an image, what kind of image it is, etc., by using some rules. Okay, by using some rules, we can see where that image is found. And there is obviously a formula method also. Many times you can use the ray tracing to locate the image in a very simple way. Now, what are those rules? So, for ray tracing, you can locate an image, and its nature. Nature means whether it is magnified, diminished, erect, inverted, real, virtual, that kind of thing. You can locate an image and its nature by one of the following two ways. One is using ray tracing, the ray tracing method, where you will be seeing the rules. This is more of geometrical, or I would say by drawing and some kind of geometry. But if you are not interested in that, the second best method, and which is what we'll be using most often, is using the formulas, mirror formula. So this is basically your analytical method, algebraic method, where formulas are there. You put the values and you get the answer. Okay, first we'll be seeing ray tracing, then we'll go to the formula method also. What are the rules? Like I said, there are some rules. See, I will show you for concave mirror first, and then I'll show you for convex mirror. It's the same thing actually. On this side you have concave, okay. This side you have, let's say, all these are concave mirrors. This side, this one is convex. If you show a ray which is coming parallel to the principal axis, after reflection, what should it do? It should go through the focus. Simple. If a ray is already going through the focus, then exact reverse. After reflection, it should go parallel to the principal axis. Kind of makes sense. Imagine this same line. If the ray reverses the direction, the ray is going through the focus. After reflection, it will become parallel. Because if it was incident parallel, after reflection, it will go through the focus. Making sense? So these are the first two basic rules. Another rule is, if a ray passes through the center of curvature, then it will retrace back the same path. So if a ray is going along the principal axis, it will just come back along the same path. Same thing is applicable for convex also. As you can see, if a ray is incident on the center of curvature, it will retrace the same path. Ray is incident on the center of curvature, it will retrace back the same path. Okay? Yeah. Can you just draw this? Or yeah, you can draw this. Anyways, you are going to get the notes after some time. It will be there in the description box and in the comment section. But I would suggest please draw it. Now, let me show you how we can use this particular ray tracing for solving the questions. Say for example, I tell you, listen man, we have a convex mirror. Okay, we have a convex mirror. This is the principal axis. And let's say we have been told, listen, there is an object present over here. Can you locate where that image will be? There is an object. Okay. First, I will say maybe this is the center of curvature, because I can feel it. Most likely it is somewhere here, because if I imagine that sphere, somewhere the center will be somewhere maybe over here. If this is the center of curvature, exactly in the middle, we will have the focal point also. We'll also have the focal point. This is obviously the pole. Okay. Now you can show multiple rays. You can choose which ray you want to show. Let's say I start off with a ray which is parallel to the principal axis. What should it do? It should pass through the focus, but since it's a convex mirror, it will be diverging. So it will feel as if it is diverging from this particular location. Okay, it will feel. So I will make this line dotted, because it is not actually entering here. It is just getting reflected from this particular point. So this was one ray which was parallel. it got reflected like this. But like I said, we need two rays to locate an image. So we'll show one more ray and my job will be done. How about showing a ray which is incident on the center of curvature? Then what will happen? It will retrace back the same path. It will retrace back the same path. So I'll make this particular line dotted over here. Okay. So this ray which is incident, after reflection here, it will again come back via the same path. Now just look at the reflected ray. The reflected ray is going like this and it is going like this. These are the two reflected rays. They will never meet. So to make them meet, I will extend them backwards, which it is already done. As you can see, they are meeting somewhere over here. They are meeting somewhere over here. So this is where my final image will be formed. As you can see, the image is definitely erect. The image is erect. It is also smaller than the object. That means it is diminished. It is diminished. You can see I had to extend the rays and it is also behind the mirror. So if it is behind the mirror, that means I can see it inside the mirror. So it is not really formed in front of me where I can take a screen and project it, but it is behind. I can directly see it through my naked eyes. So it is definitely virtual in nature. It is definitely virtual in nature. That is how you use ray tracing to locate any kind of image. I can show you more examples. Let's say of a convex mirror like this, concave mirror like this. Let's say we take the example of a concave mirror. Okay, we have a principal axis over here, and then let's say we have the object present over here. Okay, some random object, maybe I'll take it here. Okay, take this particular thing as my object. I will say the center of this mirror is somewhere here. This is the center of curvature, and exactly in the middle, somewhere you will have the focal point, correct? This will be the focal point. I want to see where the image will be formed. Use the rules, as simple as that, nothing great. So let's say we take a ray which is parallel to the principal axis. That is always the easiest one to follow. If you take a ray which is parallel to the principal axis, after reflection, what should it do? After reflection, where should it go? It should pass through the focus. So let's make it pass through the focus. It will go like this. Okay. Now show the arrow marks. A ray parallel to the principal axis reflects back from the focus. If a ray passes through the focus, it will become parallel to the principal axis. Oh, that is also there. If a ray passes through the focus, then after reflection, it will become parallel to the principal axis somewhere over here. Oh, nice. Perfect. And then you can see it is going like this over here. It is going like this over here. You can see these rays are meeting somewhere here. So I think that is the location where my final image will be formed. So this is the location where my image will be formed. Image will be formed. It is beyond C. As you can see, this is the object. The image is slightly bigger and it is also inverted. So I will say the image is inverted in this case. The image is inverted in this case. It is also enlarged because it is bigger than the object. It is magnified. And because the rays were actually meeting, so it is on the real side. So to locate or to see the image, visualize the image, I will have to take a screen, some kind of a screen over here and place it. I will see the image of this object on the screen. It will be inverted and big. In this case, I did not need a screen. It was virtual. I could directly see it inside the mirror. Got it? Yes, Shreyas will be having AC and EM waves after ray optics and everything. Okay, not now. I want to actually finish rotation and SHM first for us to start AC and EM waves, because the concept of phasors will come over there. So actually I want to finish that. So I'm taking ray optics and rotation parallelly, and after that I will finish SHM, and then I will go to EM waves, everything in general, because that 11th standard topic is very, very important. Okay, cool. So I have just drawn those ray diagrams for you already in this beautiful slides. Check it out. If the object is really, really far, then the rays will come and meet at the focus. So at infinity, it will be a very small point size kind of an image. If you bring the object closer, but it is beyond C, it is not closer, it is beyond C, you will see the rays will meet somewhere between C and F. The image is inverted and smaller and real. So real, inverted and smaller, diminished. Okay, if the object is beyond C. This is all for concave mirror. If you place it exactly at the center, the ray will meet again at the center. So you can see the same size, but it is inverted. So at C, the image will be inverted, real, and it will be of the same size. It will not be magnified. Okay, it will be of the same size. If you bring the object further closer between C and F, which is what we had drawn, then the image is inverted, it is bigger, and it is real. Real, inverted, and magnified. The image is formed beyond C. So as you get the object closer and closer, the image moves farther and farther. It was initially at F, then slowly it comes between C and F, then it comes to C, then it goes beyond C and becomes bigger. So now, if you finally place the object at focal length, the image will be formed at infinity, means it will not be formed. That is a polite way, mathematically polite way of saying it is not formed. It's like saying, yes, I will give you 1 million rupees when time will be equal to infinity. It means, politely I am saying, I will not give you any kind of money. When will time be infinity? Never. Okay, it is not a pure number, right? It is just a concept. But if you now take the object further close over here between the focal point and the pole, notice what one big change happens. The image goes onto the virtual side for a concave mirror. It is enlarged. It is erect. It is virtual. It is virtual, erect, and enlarged. This concept is what is used by this mirror, shaving mirror, and also the dental mirrors which dentists will use. Yeah, this is a concave mirror. And if I don't know whether you can see this. Oh, I think you can see my ear. Oh my God, you can see my ear. You can also see the camera over here. So I hope you are able to see. This is making an enlarged image of me. Enlarged image of me. Yeah, because the object, I am closer than the focal point and I'm between the pole. So the focus is somewhere after me and between the focus and that pole. That's why you are seeing an enlarged image. You can see that right over here. Okay, this is how it is. And somewhere the focus will be, you can see somewhere the image will disappear. And once that image disappears, that point is where no image is formed. And I am placing myself at the focus. So the image will be formed at infinity. Is this clear? Amazing. Thank you, Sujit, for all the love from Tamil Nadu. Thank you, man. Thank you so much. Okay. Same thing we can also say for convex mirrors. But for convex mirrors, the image is always going to be diminished, erect, and virtual. That is the best part. Only when the rays are parallel, that means the object is very, very far, then the image is going to be virtual and it will be very, very point size. Like, you are taking maybe a monster or an elephant or a dinosaur, which is very, very far. If you have a convex mirror, then a small image of that dinosaur or that monster will be formed in that convex mirror. Convex mirrors are used in your parking lots, or you can think of the other side of the spoon, or in many places where they want to, or even your rear view mirror of the car. Yeah, that's a convex mirror. Or your bike, it has a convex mirror. What happens is, imagine you are riding a bike. This is your rear view or side view mirror. There is some truck behind me or some car coming behind me. Then this is the object. Okay, a small image, virtual, is formed. That is why we use convex mirrors, because you can see concave mirrors most of the times, except for this, makes real images. Makes real images except for this, which is very, very close object only. So why do we need the virtual image? Because obviously, imagine if it's a rear view mirror, I can't expect a real image, and I will say I will hold a screen over there and then I'm going to see the truck which is there behind me. Proceed, man, directly. I don't have so much time and patience. So we have a virtual image, and that virtual image is going to be very, very small. You can see it diminished, but good part, it is erect. If it was inverted, that is a headache for me. Imagine a truck is coming from behind. and I'm saying an inverted image of the truck. I am like, wait a minute, what is that? Truck is opposite like this, huh? It is going left, it shows going right. I'll be so confused. So luckily for us, it is erect. So I get a true sense of what is exactly happening behind me. But because it is diminished and the images are formed so close, imagine one more truck is behind here, that image will also be formed here. One more truck is here, the image will be formed here. One more truck very far, image is formed here. All those trucks which are behind me, all those images are formed here. So you lose a sense of depth. You feel, oh, that truck is also here only. This close truck is also here only. Oh, maybe they are, very, very far only. So that is why a warning is written on the side view mirrors that the objects in the mirror are closer than they are perceived or appear. Getting my point? So why they write that? Because you might feel that the object is far because, oh yeah, the truck is coming from that time or one car is coming from that time in my mirror. I'm not seeing it move only in the mirror because it will have barely this much space between focal and the pole point to change its location. So you might feel it is not moving, it's not coming close. So you might lose a sense of depth. So that perception might not be there and you will perceive that maybe that car is still or the truck is far away. So that's why that warning label is there. Objects in the mirror, that means the image which is formed by the mirror is actually closer, maybe actually closer than what it seems to be. Okay, how many of you understood this? Yeah, experimental physics is already there and I have done that lecture. Just search for experimental. It's a beautiful class. Not every time a question comes, but if it comes, you can just watch this class. It's 3-hour class. All experiments I have done with question practice. Concept question. Usually one question maximum might come, not very high weightage. Okay, fair enough. Okay, Williams, let's move now to the next important thing, and that is the sign convention, bro. Every time I've seen sign convention, people make so many mistakes because they don't know only what is the sign convention. Okay, I'll tell you first. There are couple of things: focal length, radius of curvature, radius basically, object distance, and image distance. Okay. So, first of all, let me write it down one by one. F, which is the focal distance, is actually the coordinate of the focal point. R, which is radius of curvature, is actually the coordinate, like you have coordinates, right? 2, 0, 5, 1, like that. Coordinate, but here we only take x-axis coordinate of center of curvature. U is basically the coordinate of object and V is actually the coordinate of image. I'll tell you why the confusion happens is because object distance. The moment you hear the word distance, what comes to your mind? Scalar quantity. And distance is like an absolute number. You think of a positive value. But then object distance can be positive and negative. And people get confused. Distance are like this or like this. Which right or left is positive, negative? See, don't go like that. Look at the coordinate where the object is placed. Say, for example, maybe over here. The object is here. So we need to check the coordinate. Okay, the coordinate is -3. Okay, like that. Okay, or maybe in this scenario, here the object is here. Maybe the coordinate is -2. You can see the image. It is maybe +5. So coordinate is what the distance is. Don't get confused by the word distance. For focal length, use coordinate of the focus. For radius, don't look at the radius because a lot of time people see radius of curvature. They look at this arrow mark. Oh, sir, radius is like this. It is going this way, positive. No. Don't do that. Don't show only any arrow mark on the radius. This is just a line. Don't show any arrow mark. See where the center is. and check the coordinate of the center, negative, positive, etc. Sir, but how do I know which ones or which side is negative or positive? See, the principal axis, you will take it as your axis. The principal axis as your axis. So keep this in mind. So your principal axis is your x-axis, which is the main thing for all these things over here. And the pole is the origin. Pole is the origin. And upwards is taken positive, and downwards we will always take it as negative. Now, in the principal axis, which is the x-axis, which side is positive x and which side is negative x? Is it right or left? For that, check the incident ray. Wherever the direction, the direction, the direction, the direction, the direction of incident ray, forget what happens to the reflected ray. Incident ray, the direction of the incident ray points towards positive x-axis, points towards positive x-axis, positive x-axis. So if an object is here, the incident ray, IR means incident ray, is going like this, it is pointing this side. So this side of the pole is positive. So that is why this is positive and naturally this is negative. If you go over here, as you can see, the object is placed here. The rays are going like that. The incident rays are pointing towards the positive side of the x-axis. So this is positive side, this is negative side. Is that absolutely clear? No. Yes, it gives you headache. Now it will be very clear. That is why I will give you examples now. I will give you examples now, okay, on sign convention. Observe this carefully, one by one. Okay, we'll take many examples. I want everyone to be absolutely clear about this. We'll take many examples. Don't worry. We'll take concave mirrors also. We'll take convex mirrors also. Okay, we'll take concave and convex both, so that you are absolutely very clear. It's just that this is also convex, this is also convex, but they are facing on two different sides. That's the only difference. And I want you to be comfortable with everything. Okay, so let us see in each case what happens. Say my object is here. Say my image is here. Say my object is here. Say my image is over here. Say my object is here and image is here. Say my object is here and image is here. Then I say this is the center of curvature. This is the focal point. This is, let's say, focal point. Let's say this is center of curvature. Chumma, some random things I'm showing. Okay. This is focal point or whatever. This is focal point. This is center of curvature. Okay. Some random places I'm showing it, nothing else. Okay. Focal point. This is center of curvature. Okay. Then here also, let's say we show there is an object here and the image is formed over here. And I don't know, Chumma, I'm saying this is focal point, this is center of curvature. Let's say in this case, maybe the object is here and image is formed over here. Maybe this is focal point, maybe this is center of curvature. Okay. Then let's say this is where the object is This is where the image is, and maybe this is center of curvature, maybe this is focal point. Okay, forget the last one. In every single case, I just want whether object distance, image distance, radius, and focal length, whether they are positive or negative. F, R, U, V. That's all. I'm just interested in these quantities, nothing else. So what happens to focal length? What happens to radius of curvature? What happens to U? What happens to V? F, R, U, V. That's all. Focal length, radius, object distance, image distance. Focal length, radius, object distance, image distance. That's all. Focal length, radius, object distance, image distance. Focal length, radius, object distance, image distance. Focal length, radius, object distance, image distance. After solving these problems, trust me, you will never ever have any kind of doubt. Okay, ready for this? This is given to me. Okay, now I'll create a duplicate. Let's solve this. First, look at the incident ray. Okay, where is the incident ray coming? If this is the object, it's front of the mirror, the rays will come like this. The rays will obviously come out like this. So which direction are the rays going? This side. The pole is always considered as the origin. Origin, pole is the origin, origin, origin. So whichever side the incident rays go, that is the positive side. So naturally, I have figured it out that this is the positive side by sign convention and this is negative side. Object is here, so the ray will definitely go like this. The ray will go definitely like this. So it is going this side. So this side will be positive, this side will be negative. Here, the object is here. The ray from the object will come like this. So it is going towards this side. So this side will be positive, this side will be negative. In this scenario, the object is here. The ray will come and hit the reflecting surface before being reflected back. It is pointing towards this side. So this side will be positive and obviously this side will be negative. So first things, which side is positive and which side is negative, that is clear. Everybody till this point? Okay. Awesome. Awesome. Laptop, what is my favorite car and plane? My favorite plane, though, I can tell you, it is the Concorde plane, which is no longer operational, but I love the Concorde. It was supersonic with 4 jet kind of engines and passing over the Atlantic. I really love the shape and the kind of plane it was. And if you talk about the car, obviously the I would say Aston Martin. I really love Aston Martin, and yeah, it's one of my favorite ones, and especially in the shades of green. I really love it. Yeah. Okay. Moving on now to the question. Oh, yeah, it goes like Mac 2. Perfect, Sujit. Till this point, clear. Okay. Sir, what is the angle between lens and principal? Lens and principal axis means? I didn't get you. How can there be an angle? Okay. So, coming back over here, what are the signs? For F and R, what did I just say? For F and R, look at the coordinate of F and C. Coordinate of F and C. F is on the negative side, as you can see over here. So the answer will be negative for F. Radius of curvature, look for center of curvature. This is radius, but the radius's center is over here. So it is on the negative side. So this is also negative. Same thing over here. F and C both are on the negative side. So this is also negative. This is also negative. Over here, focal length and radius. For radius, look at center. Center is on the positive side. So this is positive and this is also positive. Here, both F and R again are on the positive side and this is also positive side. Is this absolutely clear? So in a way, you can say for concave mirrors, focal length is negative or radius is negative. For convex mirrors, focal length and radius are positive. You can see it very, very clearly. Is that understood? Yeah, perfect. Thank you, laptop. You are in VID Chennai. I'm so glad and I'm so happy for you. All the best for your first year. Enjoy fully and God bless you, my dear. And hopefully, you will get a very great company and you will prosper all the 4 years in all the amazing clubs, making new friends. Okay, all the very best. and glad you came back to say hello and a word of thanks. It means a lot. I become very happy that day. Okay, it means a lot. Okay. Now, if you talk about object distance and image distance, look at the coordinate of the object. The object coordinate will be negative, as you can see. Image is on the positive side. So positive coordinate, like image coordinate will be like 4, 0. Object coordinate will be like minus 5, 0, like that. So that is what I mean. Look at the coordinates. So this will be obviously positive. Here, object and image both are on the negative side. So this is negative. This is also negative. Over here, object is on the negative side and image is on the positive side. Over here, object is on the object is on the negative side and image is on the positive side. That's how simple it is once you know which side is positive and negative. Is it clear? You just need to look at the coordinates. Now, this problem is slightly even more trickier and you will see why. This problem is slightly more trickier. Okay. First of all, we need to figure out how the rays are coming out from the object. Lot of people are going to do this and this is wrong. Can you think why? Look at the question carefully. This object is behind the mirror. It's like saying this mirror is there and one object is there behind it. Can it even reflect? No, right? Because this part is flat or whatever, opaque. So this object is not a real object. It means it has been created virtually. So it is a virtual object, guys. This is the common mistake which many students make. So the rays are actually coming like this to make that particular object. Keep that in mind. So the rays are actually coming onto the object like this to make that object. So now incident ray is going this way towards the positive side. So this is positive. Remember, pole is always the origin. Pole is always the origin. Pole is always the origin. Got it, everyone? Till this point, absolutely clear? Perfecto? Okay. Similarly, now look over here. The object is in front of the reflecting surface, so we are safe. So if a ray will go like this, it will definitely get reflected. So we have nothing to worry about. So this side will be positive, this side will be negative. Okay. What about this particular mirror? The object is behind the mirror, so definitely it is virtual in object in nature. So a ray would probably be incident like this. Since the incident ray is going this side will be positive and this side will be negative. Whichever side the incident ray is going. And give you one more example of that. Imagine our object is over here and maybe image is formed over here. Maybe I'm putting focal length is here, center of curvature is here. This is a convex mirror again. And again, I'm interested in focal length, radius, object distance and image distance. Look at this. Object is behind the mirror, so it can't emit the rays and get reflected. So rays would be falling onto it like this. So the rays will be actually falling onto it like this. So that means this side will be positive and this side will be negative. Is this part absolutely clear? Yeah. Yeah. Very good, Williams. Awesome. Awesome. Now let's get the signs right. Okay. Concentrate on the class. Don't ask any other doubts. Focus, guys. F and C. Okay. This is obviously negative side if this is positive. F and C are on the negative side. So this is negative. Radius is also negative. F and C are on the negative side. So this is also negative. This is also negative. Where is F? F and C are on the positive side. So this is positive. This is positive. And F and C are on the positive side. So F is also positive. R is also positive. So convex mirrors, focal length, whether it is real object or virtual object, focal length is always positive. Concave mirrors, whether it is a real or virtual object, it is always going to be negative, as you can see over here. Focal length and radius is always going to be negative. So the only difference is this object over here. was virtual. Virtual. This was real. This object, because this was dotted line, this is virtual. It is not real. Even this object over here was virtual because this dotted line is there. Everything else was real. Last thing, object distance and image distance. Object is on the positive side, image is on the negative side. Object is on the negative side, image is on the positive side. Object is on the positive side, image is on the negative side. Object and image both are on the positive side. That's how you solve the question. I think after this, there cannot be any doubt for anyone. Okay? Everyone with me on this? Everybody got this concept clear of how the sign convention works? Simple rules. Okay, and it is always about the coordinates. Don't think of it like distance, because distance word only is confusing. Think of it like coordinates. I have done it for real and virtual objects both. Now comes the graphical part. Very interesting how the graph looks like if you plot object distance versus image distance for concave mirror and for convex mirror. Now you can do it mathematically by the mirror formula also, but I mean, just look at it over here. Say, think like this. Okay, think like this. Go back to maybe first concave mirrors. When the object is very, very far, the image is formed at focus. And as the object comes closer, the image starts to go away from the focus towards infinity. And finally, when it comes to center, it is also at center. And as it comes closer and closer, you will see that it moves farther and farther. Correct? Now the point is, as long as you see the object and the image are over here, object and the image are over here, object distance is negative, image distance is also negative, and it will be a curved line. It will be a curved line. Object distance is negative, image distance is also negative. So look over here. This is the part that you should be concentrating on. Object distance is this, image distance is this, it is negative. You can see it is a curved line, and observe this very carefully. When my object distance is infinity, so when object is at infinity, where is my image being formed? The image is being formed at focal length. The image is formed at the focal length. Kind of makes sense. That is why it is becoming like an asymptote over here. So when the object distance is negative infinity, that means you are very, very far away. Over there, the image is formed at minus f. So that is why the graph becomes like an asymptote over here. It becomes like an asymptote over here. Is that making sense? Similarly, when this u, which is object distance, will become minus f, object distance will become minus f. That means the object is very close to f. If the object comes very close to f, image will be formed very, very far away at infinity. That is why you will see that the image distance is going to infinity, but actually negative infinity, because on this side is negative, this side was positive. Are you seeing why the graph is like this? And the graph also becomes symmetrical. So whatever happens here, you will see an exact replica on the other side. You will see an exact replica on the other side. Yeah. Everyone with me on this? Pakka? Let me know quickly in the chat box. Let me know, guys, quickly. Not able to see your chats for some reason. Let me just check. 1 second, guys. Yes, now I can see. Thank you. Okay. Somebody was asking, who is this? Rama. Is this hyperbola? Yes, this graph is a hyperbola. This is a hyperbola. Okay. Good, you guys noticed it. I'm not sure whether conic sections is done, but yeah, this is a hyperbola. Okay. Now, if you look at the same graph for convex mirror, convex mirror, things are slightly almost similar but slightly shifted. It's like the same hyperbola gets shifted over here. Okay. So what happens is, for convex mirror, I have already shown over here, if the object is in front, the image is virtual diminished in the other side. So object distance is negative, image distance is positive. Object distance is negative, image distance is positive. So use this concept over here. Object distance is negative, image distance is positive. That is basically this part of the graph is what we are talking about. Okay, and it continues over here and continues like that. But observe this carefully. When finally my object, this is object distance, object is at infinity, you will see that this particular graph, you will see that this particular graph goes like this. Okay, this particular graph goes like this, and it will start touching over here, which is basically image will be at focal point. Makes sense? If the object is very, very far away, the image will be formed on the other side, positive f. That's why you can see plus f over here. Object distance is negative infinity, image is formed on the focal point. Are you seeing that? That's very, very interesting, guys. So that is one aspect which you should know. Again, this is obviously a hyperbola. This is a hyperbola. It passes through the origin. It has to, because if you place an object on the pole, the image will be also formed at that same place. So the graph will definitely pass through the origin. Same thing will be here, because this graph is not going, the other half of the hyperbola will have to pass at the origin. Always, always, whether it is convex mirror or concave mirror, one part of the hyperbola, either this part or that part, will pass through the origin. Because if you imagine, take an object and place it very close to the mirror. I hope you are able to see this. See the nib of the pen? Where is the image formed? See, where is the image formed? It is formed on that mirror only. It is formed on the mirror only. So object at the pole, image is also at the pole. You can see the very clear demonstration over here. So that is why one part of that hyperbola will pass through the origin no matter what. Yeah, perfect. It's okay, Deepan, you can skip it. Not an issue. It's not needed. I hope you are able to visualize these graphs. A lot of people just had this graph, oh, like this, or like this, or concave mirror. Don't do such stupid things. Understand why it is the way it is. If you don't get it, then you are doing a wrong thing. You have to study it properly. Okay. Now, we usually don't study this part, because then object distance becomes positive. That means it will become virtual object. So this is the virtual object scenario. Same thing over here also. When u becomes positive, you will see it will become the virtual object scenario. So usually we don't draw for virtual objects. We can directly do it by formulas. Okay. So now that the graphs are done, now let's go to the final part and then do the mirror formulas. Optical power, power of a mirror. What is the meaning of power of a mirror? What is the meaning of power of a mirror? Okay, let me show this to you. Imagine there is a, oops. Imagine there is a mirror like this versus a mirror like this and a mirror like this versus a mirror like this. Okay, principle, 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 principle. No longer scared of the principle. Okay, if you look at the rays which are parallel for a concave mirror, okay, probably they will come like this, and maybe they will meet over here, somewhere like that. Here, the same rays, you will see probably they will meet over here, like this. Here, The rays which are parallel will obviously get diverged. It's a concave mirror, sorry, convex mirror. So they will get diverged. I'll have to extend the rays to locate where exactly they are meeting. 1 second. I will first show the extension, then I will show the rays. It is always easier that way. Okay. Reflecting like this. Here you will see those same rays, probably they will meet somewhere over here like this. As you can see in both these mirrors, this is concave, this is convex. This side is concave, this side is convex. The convex is diverging in nature, diverging in nature. The concave is converging in nature. Whenever a mirror is converging, the power is positive, and whenever it is diverging, it is negative. Anything converges, positive. Diverge, you are spreading it, negative power. Simple. So, if you ask me the power formula, or sorry, the power value in all the scenarios, approximately qualitatively, this power will definitely be positive, I will say, positive power. This will be also positive, but this will be definitely negative and also negative. One thing is clear, positive means converging. So very, very important. Positive means converging, and negative means diverging. So if I tell you the power is +7, it is concave, converging. If I tell you the power is minus 0.7, then it is diverging because negative. Next thing, as you can see, the rays are meeting after a long time. Here the rays are meeting quickly. So this is more powerful. This is diverging from a large distance. This is from a short distance. Quickly it is diverging. So this has larger power. Even this has more power. This has less power. So in both these scenarios, I will say the magnitude of the power is going to be less. But here the magnitude, I'm not talking about the sign value, magnitude of the power is going to be more. Not just that, notice how the focal length is more here. So here the focal length is more, whereas here the focal length is less. This gives me a good idea that focal length is definitely now related to power. Focal length is definitely related to power. Can you see that? Less focal length, more power. Less focal length, more powerful. Big focal length, less powerful. So that gives me an idea of the optical power of a lens. So power, magnitude wise, will be inversely related to the focal length. More power, less focal length. Less power, more focal length. Okay. Not just that, see over here, focal length is negative, but power is positive. Focal length is negative, power is positive. Focal length is positive, power is negative. Focal length is positive, power is negative, which means the signs are opposite. So I can't just put 1 by f, I'll have to put minus 1 by f. If f is negative, p is positive. If f is positive, p is negative. So this is the right formula for power. Now, the unit of power also very important. If F is measured in meters, SI unit, then power is measured in diopters. It is measured in diopters. Cool? Clear? Understood? Shall we go ahead? Shall we go ahead? Things big than the verse. Join the batch, man. Then I will answer all your queries one by one or put it up in the comments. Okay. So we have amazing Sigma batches, Ekalavya batches. Be a part of it. We also give you doubt facilities, Telegram support, or even in the class support and all of that. So be a part of it. Then I can answer all your doubts one by one. Cool. Now, let's imagine a question based on this. Let's imagine a question based on this slowly, one by one. If I tell you the radius, the radius of concave mirror is 25 centimeter. Find focal length and power. Find the focal length and also the power of it. Let's do this very quickly. Radius is given, find focal length. We all know radius is 2 times of f. Radius, because it's a concave mirror, do not forget, it's a concave mirror. Center of curvature will be here. This will be the negative side. This will be the positive side. Focal length will be also on the negative side. So technically speaking, the radius is not 25. Lot of people make this mistake. It is negative 25. So this is nothing but 2 into f. Therefore, our focal length is minus 25 by 2, which is minus 12.5 centimeters. Is that absolutely clear? The focal length is minus 12.5 centimeters. Next thing is the power formula. For that, I will just use minus 1 by f. So it will be negative 1 by focal length is minus 12.5. Oh, but wait a minute, sir. You cannot use 12.5 because it is in centimeters. So first thing we'll do is we'll convert it into meters. It is minus 12.5 divided by 100 meters. Minus 12.5 divided by 100 meters. But I don't like that number 12.5 because I want fractions over there. So I can write it as minus 25 by 2 and 1 by 100 meters. It looks great. 25 goes with 100 4 times. So it will look like this, minus 1 by 25 goes with 100 4 times, 4 2s are 8. So minus 1 by 8 meters. This looks good to me. Now I can put the focal length as minus 1 by 8 over here. Minus 1 by 8 because now it is in meters. Remember, SI units for power. So minus minus becomes plus, 8 goes on the top. So the power will become 8 positive diopters. Because it is positive, it means it is converging in nature. It is converging in nature. Got it? Let's do one more question coming up on your screen. If power is minus 2 diopters, find radius and focal length. Find the radius and the focal length. Okay, let's start. Power is given, focal length will be easier to find. Power of a mirror is minus 1 by f. Power is given to be minus 2. So this will be minus 1 by f. Minus minus cancels. So f will be 1 by 2. Therefore, this is in meters. It's as good as saying 0.5 meters, which is 50 centimeters. So the focal length is 50 centimeters. Okay. Next thing, we'll find the radius. Radius is 2 times the focal length, and focal length has come out to be positive. Use it as it is, 2 into 50, which is 100 centimeters. This is obviously a convex kind of a mirror because focal length, radius, everything is positive. Okay. All right. Megasham, the giveaway is ending tomorrow. All right, because we launched one more contest via MVSAT. So tomorrow the contest will end, and day after tomorrow we'll declare the winners. Got it? Fair enough? All right. Awesome. Awesome. Optical power done. Where is it? Mirror formula slide. Oh, my bad. It went here. Okay. Now let's go to the final formulas and then we'll start with the final set of questions. Mirror formula. Remember, just some time back I had told you there are two methods to locate where an image is formed. One is ray tracing via drawing and second is formula. Ray tracing we just did like this. Okay, this was the ray tracing. But the other method is via formula. So what is that formula method? Let's come to that. Okay. So the formula is very simple, guys. 1 by V plus image distance 1 by U, which is object distance, is 1 by F. F is the focal length. So that is the mirror formula. You tell me where the object is, where the or how much the focal length is, I can tell you where the image is formed. Very simple. Everything is sign sensitive. So keep this in mind. This is a sign sensitive equation. Sign convention has to be followed. Sign convention has to be followed. It is sign sensitive. The next thing is magnification. Now, what is this magnification exactly? First, let me explain that to you and then I'll tell you the formula. It's not that difficult. Magnification means how many times is the image as compared to the object. So, magnification, the symbol is this. It is the size of image. It is the size of image upon basically the size of object. Size of object. But remember, magnification can be more than one, less than one, positive or even negative. So what does it exactly tell me? So let me give you some examples over here. Say for example, magnification, I tell you, is +2. Magnification, let's say, is -3. Magnification, I tell you, is +1. Magnification, I tell you, is -1. Magnification, I tell you, is plus 0.6. Magnification, I tell you, is minus 0.3. So many values. What does it mean in each and every case? Let's go one by one. First scenario. When magnification is +2, positive means it is erect. Positive means it is erect. 2 means it is enlarged. It is bigger. Image is bigger than the object. Minus means the image is flipped. It is inverted. So wherever you are seeing positive, it is nothing but erect. This is also erect. This is negative, so it is inverted. Inverted. This is negative, so again it is inverted. This is positive, so it is nothing but erect. So image and object are in the same direction, pointing towards the same direction. Now, if it is having a value which is bigger than 1, like the 3, forget the sign, it is enlarged. So 3 is bigger than 1, so it is obviously going to be enlarged. 0.6 is less than 1, so image is 0.6 times of the object, so it is diminished. It is diminished. It is diminished kind of image. 0.3 is also less than 1, so it is diminished. Forget the sign now. It is diminished. -1 and +1, be careful. 1 means it is neither big nor small, so it is definitely going to be of same size. It is going to be of same size. So whenever we find the nature of the image, we get the erectness or the inversion via magnification. Also, whether it is enlarged or diminished or same size via magnification. Whether it is real or virtual, we get to know from V value. So, if V value is positive, then it is on the virtual side. And if if V value is negative, then it is on the real side. If V value is negative, that means the rays are actually meeting over here on the negative side, then it is a real image which is formed. So this is how you can get a complete picture, whether it is real, virtual, erect, inverted, enlarged or diminished. Okay, perfect. Everyone with me? Everybody with me? So this is magnification's definition, size of image by the size of object. Now what is the formula to locate the magnification? So keep this in mind, very, very important. Second. If you look at the height of the image and height of the object, so let me just draw it over here. Let's say this is object, and let's say maybe this is the image. Okay, this is principal axis. Let's say this is HO. This is width of the object. This is height of the image. This is width of the image. Width is this, height is this. Width is always along the principal axis. So the magnification which is perpendicular, talking about the perpendicular, this is principal axis, perpendicular to the principal axis, is called as lateral magnification, and this is height of the image by height of the object. Okay, but that magnification which is along the length of the principal axis, so the magnification which is along the length of the principal axis is called longitudinal magnification. This is width of the image upon width of the object. So this formula comes out as minus image distance by object distance, whereas this comes out as minus V by U, but this square. Don't put the bracket inside, because if we square it, then it will always become positive. So this bracket, you can put it here, or minus sign is outside that. So minus V by U whole square. That's it. This is the formula for magnification laterally and longitudinally. Usually when magnification is given or asked, it is this one, not this one. If they mention specifically along the longitudinal, then use this formula. Otherwise, forget this. Usually they will talk about lateral height-wise magnification, not the width-wise magnification. Cool? Okay, perfect. Awesome. But there is something more to this. There is something more to this. Imagine, forget magnification now. Imagine this object and image, they themselves are moving. Okay, so this is my object. Let's say this is my image. This is your principal axis. This is object. This is my image. Maybe this is my object velocity. Maybe this is my image velocity. VO is object velocity, VI is image velocity. They are object and image velocities following the sign convention. Then guess what? The velocity of the image upon velocity of the object comes out exactly similar to the longitudinal magnification. The longitudinal magnification, which means if I know how much fast the object is moving, image velocity will be as simple as, minus V by U whole square. Directly you can use longitudinal magnification formula very easily. You are going to get it. Very, very important. Very, very important. So image velocity, object velocity relationship also covered. Magnification also covered. By the way, these formulas are only valid for paraxial rays. Valid for paraxial rays means for small objects and images only. Very, very important. For small objects and images. If the object is very big, very tall, then you cannot use this because the approximations are no longer valid. It will no longer be paraxial. Okay? Awesome. Darun, I'm so glad, man. You got VID Valor of CSE too. Proud of you, my dear. I hope you are excited. Yeah, computer science, all the very best. Crack it, nail it, enjoy it, and I'm super duper proud and happy. Darun, all the best, all the best. Valor CSE is really good. Okay. So magnification done. Okay, let's probably do some questions on this. let's say I tell you there is a concave mirror, okay, and I tell you the focal length is example 20 centimeters, and let's say we have an object over here, and let's say that object is kept in front of it, at a distance of maybe 60 centimeters from the mirror. Question is find the image and its nature, everything about the image. Basically, try to find out every single detail about that particular image. Okay, that is the question. So let's try to do this. Find every single detail about that image. Okay, first of all, let's establish the sign convention. It's very important. Without that, we cannot proceed. So as we can see, the rays will go like this. So obviously, this side will be positive side, this side will be negative side. The center of curvature and the radius of curvature will be on this side only. So this will be focal length, this will be center of curvature, everything is on this side. Okay, so let's use maybe mirror formula and then we'll get everything. Okay, so here object distance is minus 60 centimeters, focal length is minus 20, radius, which is 2 times of f, will be minus 40, everything in centimeters. We got all these information right by the diagram and whatever is given. That is the first step of the problem. Now let's apply mirror formula and see what do we exactly get. So 1 by v plus 1 by u is 1 by f. Image distance I do not know. Object distance is minus 60. Focal length is minus 20. Therefore, 1 by v will be minus 60 will become plus 60. So it will become 1 by 60 minus 1 by 20. This I can take obviously LCM. 60 and 20 LCM is 60. This will be 1. 20 goes with 60 3 times. So this will be 3. So therefore, 1 minus 3 is minus 2. Minus 2 by 60, which is minus 1 by 30. So that is 1 by v. Therefore, image distance is negative 30 centimeters. Image distance is negative 30 centimeters. Okay. What can you expect from this negative 30 centimeters? Negative value. Hi, Sai Priya, very good. Negative means it is on this side. What is this side? This is real, that is virtual. So clearly, the image is not virtual, it is real in nature. That is one thing. And at a distance of 30 centimeters in front of the mirror. Okay. Next step, let's figure out the magnification. Let's figure out the magnification. Magnification is normally minus v by u. Minus v is minus 30. So I'll put minus 30 over here. Object distance is minus 60. 3 minuses will give me 1 minus and this will become minus half. So it's as good as saying minus 0.5. Minus tells me it is inverted in nature and 0.5 tells me it is diminished also. So it is diminished, it is inverted, it is real at a distance of 30 centimeters. 0.5 means if object was 10 centimeters, image is 5 centimeters, half the size. Okay, understood how to solve the basic questions? Very straightforward. Okay, let's do one more question before going to my previous year questions. Okay, let's do one more question. Radius is example 10 centimeters. Okay, and this is our principal axis. We have an object over here at a distance of 30 centimeters, and what is given to me, this object is moving like this at maybe 2 millimeters per second. question is, question is find image velocity and its nature. What kind of image is formed and what is the image's velocity? Very nice question, guys. Very nice question. Okay, let's try and solve it. Let's try and solve it. First, let's establish the sign convention. Okay, without that, we cannot proceed. Object is here, rays will go like this. So naturally, this side will be positive, this side will be negative. The center of curvature will be here. Focal point will also be over here on that side. So start off with that. Radius of curvature will be positive 10 centimeters. So focal length will be r by 2. So it will be just plus 5 centimeters. The object distance is going to be negative. It is on the negative side. So minus 30 centimeters. This is what I can interpret from the given information. Nothing more I can get. Now it's all about calculation. So let's go to the calculation part. Starting off with mirror formula. So 1 by V plus 1 by U is 1 by F. Is that right? 1 by V plus 1 by U is 1 by F. Okay. So therefore, 1 by V plus object distance is minus 30 is equal to 1 by F. F is nothing but 5 centimeters. Okay, perfect. So therefore, 1 by V, see minus 30 on the other side will become plus 30. So it will become 1 by 30 plus 1 by 5. LCM is 30. So this will be 1 plus 5 goes with 36 times. So 1 plus 6. So this will become 1 by V is equal to 7 by 30. Therefore, V will be equal to 30 by 7 centimeters. Because it is positive, that means it is going to be virtual image. Positive means it will be on this side, virtual, behind the mirror. Okay, done and dusted. Now let's go to the next part. And what is it? Magnification and everything, because nature is also asked. So the basic lateral magnification will be minus V by U. So image distance is 30 by 7. Object distance is minus 30. Minus minus cancels. 30 cancels. I'm just left with 1 by 7. So this tells me because it is positive, it is definitely erect image, but the value is less than 1. So it is definitely diminished in nature. It is definitely diminished in nature. Is that right? We got that apart? Okay. Now, that is not the end story. There is one more part to it. And what is that part? You have to locate what is the image velocity. What is the image velocity? So, for that, we had seen the formula. Velocity of the image upon velocity of the object is minus V by U whole square. Okay. What is image distance? I think image distance is 30 by 7. So I'll put 30 by 7. What is object distance? It is minus 30 whole square. Image velocity, I do not know. Object is going this side. Right side is positive. So I will put 2 millimeters per second here. So therefore, Vi by 2 will become 30 cancels, minus square is positive, so it will become 1 by 7 square. 1 by 7 square is 1 by 49. 2 goes on the other side, so therefore I will get image velocity as minus 2 by 49, but this is all in millimeters per second. So we got it. What does this minus sign tell me? It tells me that my image is not going in the same direction as the object, it is going in the opposite direction. So this is where the velocity is, left side. Cool? Pakka? Understood? Clear? Shall we go ahead to the next one? Hi Uday, welcome aboard. Nice to see all of you. I have a beautiful question. Let's see whether you guys can solve this and visualize it. I absolutely will love doing this question with all of you. Okay. See, this is the principal axis. We can take maybe concave mirror. Let's say the focal length is 50 centimeters. Let's say here we have, very, very important, we have a cylinder which is placed like so. This is a cylinder which is placed like so. And this particular cylinder is placed maybe at a distance of 25 centimeters from the mirror. There will be an image which will be formed. The axis of the cylinder coincides with principal axis. Okay, visualize this. So imagine this is the mirror, and imagine you have placed a small cylinder in front of it. There will be an image which is formed. I hope you can see that this pen is also like a cylinder. You can see the image of the pen is formed inside the mirror. Can you see that? Yes. So this pen is also like cylinder, but it is a very small cylinder. That's the only difference. Question is find question is find the find the ratio of volume of image to the object. Very interesting. Volume ratio is asked. Okay. Let me think, what exactly does that mean? Volume ratio. So, volume of image upon volume of object. Volume of the image will also be a cylinder. Obviously, some kind of a cylinder, maybe like this, right? It will be also some kind of a cylinder like this over here. Yeah. Now, that cylinder will also have some radius and some height. Some height and radius will be there. So, volume of a cylinder is pi r square, but this will be the radius of the image, into the height, but this is the height of the image, upon, for object, it will be pi r radius of the object square into height of the object square. Pi cancels, and I am left with radius of the image upon radius of the object square and height of the image upon height of the object. Interesting. This is what it has been narrowed down to. Now see the interesting part over here. Where is the radius? Observe carefully. This is our principal axis, isn't it? This is our principal axis. See where the radius actually is. The radius is like this. This is how radius is. Radius is in the perpendicular direction. But if you ask me where the height of the cylinder is, height is like this. In this direction, it is the height is along the principal axis. Height is along the principal axis. Radius is perpendicular to the principal axis. We just saw magnification exactly that way, if you remember. Lateral magnification is heights or perpendicular direction is what you have to see. For longitudinal, you have to go the width or the length along the principal axis. Along the principal axis. So, if you go back to this problem, can you guess height is along the principal axis? So, the term that we will consider for this will be longitudinal. This is longitudinal magnification. How many of you got it? HI, height of the image upon height of the object, that is expanding along the principal axis. So that is longitudinal magnification. Whereas this Ri by Ro, that is perpendicular to the principal axis, that particular term will be lateral magnification. Lateral magnification. That is the most critical step of this entire problem. Rest all is calculative, but this, if you understood it, perfect. What is the formula for lateral and longitudinal magnification? For lateral, it is minus V by U, of course, but I have to square that, do not forget it. And for longitudinal, it is minus V square by U square, but I just have to put over here. Okay, so that's it. So that is what this is. Oh, best part, minus minus anyways got cancelled. Even if minus remained, I will not worry about it. It will just affect the sign. Magnitude wise, it will not affect it. So we have v square here, u square here, v square here, u square here. So technically, this is becoming v raised to 4 divided by u raised to 4. What a question. V by 4 by u by 4. Oh, u raised to 4. Oh, what is v? Oh, that we can figure out. That is not a big deal. That is the least of our worries. We can use our mirror formula. 1 by v plus 1 by u is 1 by f. Focal length is negative minus 50. 1 by v, I do not know. Object distance is minus 25 because this is negative side, this is positive side, because the rays will come like this from the incident side. And remember, the focal point will be over here. Okay, perfecto. So solving this further, 1 by v, minus becomes positive. So 1 by 25 minus 1 by 50. LCM is 50. 25 goes with 52 times minus 1. So 2 minus 1 is 1. So 1 by 50 is 1 by v. So v will be 50 centimeters. V will be 50 centimeters. Just have to substitute that over here. Nothing more, nothing less. So this will be 50. U is object distance is minus 25. Okay. Anyways, don't worry about the negative positive signs. We just have to square it or take it to an even power. So doesn't matter. 50 by 25 is 2. So it will be 2 raised to 4. 2 cube is 8. 2 raised to 4 is 16. So 16 times. So the volume will be made 16 times. 16 times bigger. Yeah. What a question. How many of you loved this question? This is a level 2 type, level 3 type question for mains for sure. Because many students will get stuck over here only. Okay. Lot of people will get stuck over here. Yes, Sidesh, Ramya, Uday, Sai, Kambam, Darun, loved the question, I hope. Yes, perfect, perfect, perfect. Amazing. Okay, let's do some PYQs here and there. Okay, coming up on your screen. Very simple do questions. Some 5-10 minutes I will take. If you have to attend your next class, you can watch it parallelly or you can watch this part later. Okay, because I understand 8 o'clock your next class will start. Anyways, a mirror is used to produce an image with a magnification of this. If the distance between the object and the image is 40, the focal length of the mirror is how much? Okay. Magnification is 1 by 4. The focal length of the mirror is how much? Very interesting question. First of all, it is clearly mentioned the magnification is 1 by 4. So I will put m is equal to 1 by 4. Yeah, m is equal to 1 by 4. But what is the formula for magnification? It is nothing but minus v by u. So that is 1 by 4. Yeah. So therefore, v 4 times, or rather I can say u will be minus 4 times v, or v will be minus u by 4. One and the same thing. Whichever way you want, you can do it. Okay. Till this point, absolutely clear. Okay. 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 Now, what is this? Mirror used to produce object, the focal length of the mirror. Okay. So I can see all the focal lengths being positive. So I'm assuming it is a convex mirror. Okay. Doesn't matter if I take it otherwise also. This is our principal axis. Okay. Let's say this is the object. Let's say this is the image. Now this distance is given to be 40 centimeters. Now what I will do, I'll make an assumption. Let's assume this distance to be x. So naturally this will be 40 minus x distance wise. And we can see clearly the rays from the object will go like this. So this is positive side. This is obviously negative side. So if you ask me what is the object distance, it will not be x, it will be minus x. And if you ask me image distance, it will be positive, it is on the positive side. So it will be 40 minus x. So maybe I should use that over here as well. So like for example, I can say image distance v is nothing but 40 minus x and u is minus x. So u is minus x and v is nothing but 40 minus x. So this will become minus x is equal to 4 4s are 16. So minus 160 plus minus minus is plus 4x. So take this x on this side, bring 160 on this side. So this will be 5x, 4x plus x is 5x. So therefore, x will be 160 divided by 5. How much is that going to be? 160 divided by 5, my dear warriors. 160 divided by 5. Yep. 160 divided by 5. 160 multiplied 2 times. So it will become 320. So it will become 320 by 10, which is 32. So 32 centimeters. 32 centimeters. That is the answer. So the object is placed at a distance of 32 centimeters, but that is not the question. Question is find focal length, boss. Oh, focal length. Huh? So I can use this 1 by v plus 1 by u is 1 by f. So what is v now? V is 40 minus x. So it will be 40 minus x. X is 32 plus object distance. Object distance is minus x. So it will be minus 32 is nothing but 1 by f. That's it. So 1 by 8 minus 1 by 32 is 1 by f. LCM is 32. 8 goes with 32 4 times. So 4 minus 1 is 1 by f. 4 minus 1 is 3. So 3 divided by 32 is 1 by f. Therefore, f is nothing but 32 divided by 3. 32 divided by 3. Yes, perfect. So 32 divided by 3, how much will it be, guys? Yeah, it will be less than 11, but 10.7. Yes, 10.66 centimeters, which I can approximately say is 10.7. Recurring, it will be 10.666, but I can approximately say 10.7 centimeters. Perfect. We got the answer. So if you follow the sign conventions and mark everything properly, you are bound to get the correct answer. Else you will make 100 silly mistakes with the sign. Sign convention is the major problem. Okay, cool. Let's go to the next question coming up on your screen, and here it is. When an object is placed 40 centimeters from a mirror, the image is half magnification. To obtain magnification of 1 by 3, how much should you move the object and in which direction? 40 centimeters from a spherical mirror, the magnification is half. Clearly, it will be a convex mirror because it is diminished. Okay, or else if it was concave mirror, it will be enlarged. No, magnification is half. So it is very clear it is convex mirror. Okay, we'll solve it like this. 1 by v plus 1 by u is 1 by f. So therefore, 1 by v is 1 by f minus 1 by u. LCM will be fu. So it will be u minus f is 1 by v. Therefore, v is fu divided by u minus f. So now what I will do? Now magnification is minus v by u. So minus 1 by u, I'll take it as it is. I'll put the value of v as fu divided by u minus, sorry, it was u minus f, my bad, u minus f. Yeah, u gets cancelled. So it will become f divided by u minus f with a negative sign over here, which is as good as saying f divided by f minus u. So I got magnification as f by f minus u. Why I did it? Because image distance was not given, object distance is given, and magnification is given. So I will use this formula and I will see what will I get. Okay, I'll just create a duplicate. Okay. So I'm just going to stick with this particular formula. F by f minus u. F by f minus u. So magnification is f by f minus u. Very interesting derivation which I did because I want to get rid of image distance. It is an unnecessary headache for me. So using the first information where the magnification is half. So magnification is half, m is half. Focal length, I don't know. F minus U. Object is 40 centimeters away. That means it is minus 40 technically with the sign convention. So do the cross multiplication. It will become, therefore, F plus 40 is 2 times of F. F goes on this side. So 40 is equal to 2F minus F. Therefore, 2F minus F is F. F is nothing but 40 centimeters. We got the focal length. Why do I need it? For the other part, which is this one, when the magnification is 1 by 3. So when M is 1 by 3, when M is 1 by 3, focal length anyways will be the same. So 40 by 40 will be there. I will find out the new object distance. Okay, cross multiply. Therefore, 40 minus U is 43 is a 120. Therefore, U will be 40 minus 120. Therefore, object distance is minus 80 centimeters. So what this means is, this is your mirror. In the first scenario, object was at minus 40 centimeters. Object was at minus 40 centimeters. In the second case, the object is at minus 80 centimeters. Minus 80 centimeters. This is new position. This is new position. This 40 centimeters was the old position. Now you only tell me what have you done? You have shifted it. You have shifted it away from the mirror by how many centimeters? 40 centimeters. So 40 centimeters away from the mirror. Is that right? 40 centimeters away from the mirror. Got it? How many of you understood this question? Perfect. Give me a thumbs up, guys. These kind of questions is what you are going to get. Let's do one more question on your screen. Let's do one more question. Two identical objects are placed in front of convex mirror and concave mirror, same radius, same distance. Ratio of the size of the images is asked. Ratio of the size of the images by convex and concave mirror. Ratio of the size means ratio of the magnification at the end of the day. Object radius is given and distance is given. Okay, so I have an idea. Why not use this formula which I just derived with so much of pain and headache? M is F by F minus U. M is oh, so sorry guys. My God. M is F divided by F minus U. Okay. So let's do the first scenario. Magnification in the case of convex will be focal length. I need to figure out. Okay. Now, since radius of curvature is 12, if radius is 12 magnitude wise, focal length is radius by 2. That means it will be 6. Radius is 12, focal length will be 6. So for convex, focal length is positive. So I'll put plus 6 and minus object distance. Distance is 18 centimeters. So it will be minus 18. Can you see that? Right over here. This tells me U is 18, but it is real. So it is minus 18. Why focal length is positive? Because it is convex. That's it. Same thing when I do it for concave. Same thing when I do it for concave. I will say the focal length will be minus 6. This is also minus 6. Minus U. Object distance will still be minus 18 only. Object distance will still be minus 18. That's the only difference. Let's solve it and see what do we get. 6 divided by 18 plus 6 is 24. So it will be basically 1 by 4. Over here, what am I getting? Minus 6 divided by, this is plus. 18 minus 6 is 12. So it is basically minus 1 by 2. Now, what is magnification? It is nothing but height of the image, okay, in case of concave mirror upon height of the object. Similarly, over here, magnification in convex will be height of the image in case of convex mirror upon height of the object. Now divide this with this. That's it. You are going to get the answer. All I'm asking you is divide them. If you divide them, if you divide this with this, eventually what will happen is HO and HO will get cancelled, and on the top you will have HI of convex. On the bottom you will have height of the image of concave. Is that right? After dividing them is equal to, convex will have 1 by 4 over here, and over here what do you have? Concave will have minus 1 by 2. That's it. Now solve this. This will become 2 by 4 with a negative sign, which is minus 1 by 2. But if you ask me just the magnitude part, yeah, if you just ask me the magnitude part, you take mod value, right? Magnitude wise, magnitude will be 1:2. So 1:2 means option number 1. Is that clear, everyone? How we solved it? Yes, perfect. Magnitude 1. It is 1:2. Okay. Let's do another question, maybe. Let's do another question right over here. This is JEE 2024 question. This is also interesting. Okay. Distance between object and its 2 times magnified virtual image. Magnified virtual image produced by a curved mirror is 15 centimeters. The focal length of the mirror must be. Okay. One thing is very clear, because it is magnified and it is virtual, it 100% is a concave mirror. That becomes very obvious. Magnification happens with virtual nature. Remember the dentist mirror or shaving mirror? Only in case of concave mirror. So it is something like this. Okay. So our object might be here, and this could be the image. The distance between the object and its 2 times magnified virtual image is 15. So this is 15 centimeters. So some kind of assumptions will be needed, like this is x. So naturally this is 15 minus x and all of that. So object distance will be minus x, image distance will be 15 minus x. Why is it minus x? Because it is on the negative side. The rays from the object will come like this. So this is negative, this is positive, right? Whichever direction the rays go, that side is positive. So naturally the other side will be negative. Okay. My best songs. Watch my video which I've made on the channel, man. I don't know whether you have seen that. Somewhere I have made it. September video. Did you see my September video, guys? September. Where is September? September, man. Where is September? Ayo. Somewhere it is. Somewhere. I also can't find. Maybe it is in the video section. Watch this video. Oh my god, 50,000 views. Can I crack JEE 2026 if I start in September? Just watch this. You will get your answer. Okay? All right. Now, let's solve this now. Magnification is also given to me. Magnification is also given to me. It is going to be erect image, so +2. And magnification, do not forget, is minus V by U. So that is 2. What is V? V is 15 minus X. So substitute that over here. What is U? U is minus X. So that is 2. Perfect. Minus minus cancels. So 15 minus X by X is equal to 2. Cross multiply. So 15 minus X is equal to 2X. Take X on the other side. It will become 3X. So X is 15 by 3, which is 5. So X is 5. So we got U and V value. Now we just have to figure out focal length. So use mirror formula. 1 by V plus 1 by U is 1 by the focal length. What is image distance? 15 minus X. 15 minus X. X is 5. Okay. Plus 1 by U. What is U? Negative X. Negative X means minus 5 is 1 by F. Okay. So 15 minus 5 is 10. This will become minus 1 by 5. That is nothing but F. LCM is 10. So 1 minus 2 is 1 by F. So therefore, that will become minus 1 divided by 10 is 1 by f. Flip it, f will be minus 10 centimeters. Negative indicates it's a concave mirror. So we have that option as the third option. Is that absolutely correct? Awesome, awesome, awesome. Perfecto, perfecto. Great. So these are the kind of questions, guys, you can get. So I have kept one homework question also for all of you. Please solve this homework question. Yo, where is that homework question? Yeah, it's over here. By mistake, I have posted the answer. 1 second. Let me remove the answer. Try to solve it honestly. Even if the answer was visible, not visible, don't worry. So try to solve it. This is your homework question. Concave mirror is placed, object image distance is given, the magnification is -3, the magnitude of the radius of curvature of the mirror. So if radius of curvature is asked, focal length you have to find. The method of solving this question is very similar to the one which we just solved. This was asked this year. Okay, try it out. Answer is there on the next slide with the solution, but you will get the solution after a day with the PDF in the comment section and in the description box. So keep an eye on it. All the PDFs are uploaded on our server. So make sure you use our server to download any PDF notes handwritten properly. I give you all the notes. Use it to your advantage. Cool. So this was your Captain Shreyas. If you have not yet subscribed to the #1 JEE English channel, which is about to turn 3 lakh subscribers in a matter of days, then I think you're missing out on a lot. So please do that. And yes, smash that like button down there to show your love and affection to not just the channel, but also to me. Thank you so much, guys. Bye-bye. Captain Shreyas signing off.